In 1982, 1997, and 2015, the equatorial Pacific developed the most severe thermal anomalies in the instrumental record. These events are classified as Super El Niños because their sea surface temperatures breach a specific statistical limit, one full standard deviation above the historical mean. This scale of heat transfer restructures the large-scale movement of air across the entire planet. The textbook expectation for the humid tropics is straightforward: a near-total failure of rainfall, leading to widespread, catastrophic drought across the Amazon basin. In the Indo-Pacific, the models predict a similar collapse of the monsoon systems. These macro-level precipitation patterns form the basis for our current global climate policies, agricultural risk assessments, and ecological damage projections. But predicting what falls from the sky is not the same as predicting the water that actually sustains an ecosystem. To understand that, we have to look at soil moisture, specifically in the top 10 centimeters of the Earth. During these extreme El Niño events, we see that soil moisture levels frequently do not track the observed rainfall deficits. In hydrometeorology, this is known as decoupling, a state where the moisture in the ground begins to act independently of the rainfall patterns above it. By synthesizing advanced land surface models, it appears that localized synoptic scale mechanisms can effectively override the broader El Niño signals we've come to expect. If our climate models rely solely on rainfall as a proxy for drought, they risk missing the actual terrestrial conditions that determine how these tropical regions survive extreme heat. Proving this decoupling requires continuous global data, but measuring soil moisture in the tropics is notoriously difficult. Passive microwave satellite sensors, our standard tool for this work, cannot penetrate the dense, multi-layered canopies of tropical rainforests to reach the soil below. To bridge this gap, scientists use the Global Land Data Assimilation System, or GLDAS, which uses mathematical modeling to estimate moisture levels where satellites are blind. However, raw GLDAS outputs, like the multi-model line graphs shown here, tend to produce a systematic positive bias. They consistently overestimate the amount of water actually present in the soil. To reach an accurate model, researchers must bias correct these estimates using physical, ground-level data from specialized observation networks like FluxNet and Cosmos. When we plot these theoretical GLDAS estimates against physical in-situ data, we can isolate specific outliers, like these readings from high-altitude sites in Ecuador or seasonally flooded wetlands in Australia, that skew the global average. By applying a linear regression to filter these outliers, we arrive at a bias-corrected model with a much higher level of precision, providing a reliable dataset for near-surface moisture. Mapping a global climate event requires us to anchor these massive theoretical models to specific high-fidelity ground truths. Using this corrected data, we can isolate the mature phases of the 3 Super El Niños, focusing on the windows of October to December and January to March. We then use a K-means cluster analysis to organize these global soil moisture anomalies into 4 distinct groups. The results, shown here in the red zones of Cluster 2, identify the most consistent drying signals. As expected, these are centered heavily in the northeastern Amazon. This drying signal continues across the Pacific, impacting Indonesia and maritime Southeast Asia with severe moisture deficits. But Cluster 3 reveals a direct contrast. In Eastern Africa, we see a reliable wetting anomaly, where soil moisture actually increases during these extreme events. The most significant departure from the standard model, however, is found in the southern Amazon basin. While the northern basin dries out, the southern Amazon experiences a massive increase in soil moisture during the January to March period, completely contradicting the broad expectation of a basin-wide drought. It shows that a Super El Niño is not a uniform event. Specific regions can act in direct opposition to the primary global signal. We can prove this by calculating the ratio between soil moisture and precipitation. These maps highlight exactly where the 2 variables diverge. When this ratio is inverted, it marks a location where soil moisture is increasing even as rainfall is dropping. We see these deep divergent zones most clearly in the Sahel and the southern Amazon, where the direction of rainfall change is frequently opposite to the moisture found in the soil. Data for evapotranspiration confirms this decoupling, showing the same inverted patterns in the same geographic zones. The reason the northern Amazon dries out is that El Niño forces the intertropical convergence zone to shift northward, pulling moisture away from the region. But the southern Amazon is governed by a different driver, the South Atlantic convergence zone. During a peak El Niño, this zone intensifies, which strengthens southerly, low-level air jets across the continent. When those jets hit the massive physical barrier of the Andes Mountains, they are blocked and channeled, funneling moisture directly back into the southern Amazon basin. These localized atmospheric blockages are powerful enough to entirely override the macro-level drying signals of the Pacific. The impact of a Super El Niño on land surface hydrology cannot be accurately mapped using precipitation anomalies alone. We have to replace the blunt textbook maps of the past with this more nuanced reality of decoupled zones. Ground conditions rely on a complex physical competition between global Pacific signals and regional atmospheric circulations. Our Earth system models must evolve to integrate these specific interactions between the land and the atmosphere. To accurately project crop yields and ecological health in an era of climate extremes, we have to look past the clouds and start calibrating for the soil.